Now that you're done with homework, I want to talk about them. Problem 139, we're on page 296 of your homework, where we have, we'll start out easy, okay? The integral of a fairly simple looking thing, but nevertheless, we cannot use our old methods because there's an x squared stuck there. In any case, so we'll use our new trick that we learned, and specifically for this problem, we'll use strategy up here on the other side, strategy on page 286. Follow that strategy. We will have set x equal to sine theta. Once you have done that, then well, everything falls out nicely. The cosine theta got canceled. You integrate 1 over sine squared, which is, what is that? That's just cosecant, okay? And the cosecant squared is, as you might remember, the derivative rule says the derivative of cotangent is negative cosecant squared. That's where we got that. And then so the answer is negative cotangent theta. And of course, don't forget to plug it back in, okay? So if negative cotangent, which is sine over cosine, is equal, then you have to figure out what is negative cotangent, given that sine is theta. I mean, x is sine theta, right? Cosine theta is square root of 1 minus x squared. Therefore, cotangent, which is the 1 over tangent, which is cosine over sine. So you write down cosine over sine right here. And don't forget the minus sign, and then plus c, and you're good. So that is one short, sweet little thing. And then next, we will do problem 143. And things are getting more and more involved. Although it is longer, stuff is longer, it isn't necessarily harder, okay? It's just longer. It's like driving 1,000 miles versus driving 10 miles. And one is not necessarily harder, but if you have to drive 1,000 miles in one day, you would consider it very tough, right? But anyway, so let's look at problem 143. The problem 143 is given to you in terms of theta, but like I always say, the theta is called a dummy. The dummy, we don't care what it is. So for the purpose of this problem, I'm going to change the theta to x. See over here? I change it to x just so that we can then do substitution with theta so that we don't get and follow the strategy again on page 286 exactly. That way, yes, and don't have to, change the symbol to something else. So we'll call now this. So this is my new theta following the strategy. And that's not the same as this theta, okay? This is a new theta, just like in your class, you might have two guys named George. One George is not the same as the other George. They're not related, even though they just happen to have the same name. But anyway, so that's what I did. I followed the book and continue to call the substitution theta, because that figure everything goes smoother that way. And then so we set x equals 3 sine theta according to the strategy. And then you work that stuff out a little bit and you get somewhere. You keep working, right? And at this point, you're stuck with doing trigonometric identities. So what you're going to do is follow, at this point, you have to integrate sine cubed. So from the previous section, you learned that to do something like that, what you do is you save 1 sine theta, okay? And then you have 2 left, sine squared theta, and you convert it into cosine squared. That way, what you end up with is you have sine theta d theta, which will work as your du, okay? And then you do the substitution. I didn't even write down the u-substitution here, but that's what I did here, okay? So you write it down. I think I'm missing some parentheses. Am I? No, I'm fine. Yeah, there's no parentheses missing. So, and then you integrate each one properly, and come up with some answer that looks like this, okay? Which is, I plugged it back. So then I converted it back to x at this point. Remember, we changed this problem to x, right? So you have, what's x? X is 3 sine theta. Converting it back, then you have to figure out what x is. You have to draw that triangle again. Did I draw the triangle here? I don't think I bothered drawing any triangles. Yeah, somehow is the answer is cosine theta, and the cosine, yeah, that's because we already know what cosine theta is. At one point, right here on the other side, see, I worked out that the cosine theta is this thing. And you do it by, once you know, you don't have to draw a triangle, okay? That's, I guess, I don't know. How did I do that? Doesn't matter. I'm pretty sure I draw that triangle. The triangle which says that, well, anyway, figure out how to draw a triangle and figure out what cosine. If x is 3 sine theta, figure out what the cosine is in terms of x. So once you do that, you plug it back in. That would give you, and this answer right here, that's in the value in terms of x. Well, which is fine, but x is something we exchange. We have to revert it to the original theta. See, so that's what I did here. Don't forget to do that part. Being that I changed the original problem's name to x, so I got to go back to the original theta. So the other theta, then you plug it in and you get this thing, and that's basically the answer. However, if you compare that to the back of the book, it's a little bit different. That's because it did a little bit algebra cleanup, which I did it here, but I didn't do it in terms of theta. Okay, so be sure to remember that the x here is actually theta. I wrote that down right here. But anyway, you do a bit of algebra cleaning by factoring the square root out, so you're left with something like that, and then everything turns out okay. See, and that is the right answer. Now, in the homework, I said that 143 is done in 2 ways. The first way I tried, of course, is the method that the book taught in the section. But there is another way of doing this, if I can find it. Okay. Now, the other way of doing it is, let's redo this thing. Here's 143 redo. The redo just means that we use what we used to know. Okay, without this, even without what we learned in this section, we can still do this particular problem because, oh, well, it just worked out that way. And here's to do we use our good old-fashioned u-substitution. This u-substitution, the trick is figuring out what are we going to set u for. And there's no really precise strategy that you can go by. So u-substitution is less trustworthy or less dependable, but still, if it does work, it tends to run shorter than the other one. For example, check out this u-substitution. In this case, you let u equals 9 minus theta squared on top here, and then du is whatever, and then you can plug in. What's more interesting is theta squared then equals to 9 minus u, and that's a critical point, because with this information, then you pull this thing right out. Okay, then you have a square root, etc., which turns it into a power rule situation where you have to integrate, which of course come out very easily. And then, and then you just plug it back in and you get the answer, which I cleaned up again here a little bit. It's the same cleanup, I believe. Yeah, and then got the right answer in about half the space that it took the trigonometric method. But the u-substitution, however, is more random. It's like, what are you supposed to use for u, and will it work? So that's but in this case, it does work. So so please do this. Try to do this u-substitution as well. So next. Now, problem 145, I want to talk about it more because I ran into a bunch of interesting situations that I will show you. First, let's do the problem itself. It's the square root of x to the power 6 minus x to the power 8. And the first thing you do, of course, is to pull the x cubed out of it. Now, to pull x cubed out of it, you have to be very careful because to do this thing, you have to remember to slap on the absolute value, because if you don't, the original value is the square root of something, so it's always positive. If you don't slap the absolute value on the x cubed that you pull out, part of it is going to be negative, and we'll see that in a second. That what that means is that your answer has to come into 2 parts, for when x is positive and for when x is negative. So, but for now, we'll just pretend x is positive until we find the antiderivative, and then we'll worry about whether it's positive or negative. Okay, so let's get the answer first. So we are following the strategy on page 286 again, and where x equals to sine theta, And then, of course, cosine theta is equal to the square root of 1 minus x squared, and so on. And again, we have to worry about the sign when you x cubed is absolute value. But after that point, I decided we'll not think about that for now, okay? And just focus on getting this integration out, but not forgetting that there is that situation that we have to take care of. But in the meantime, so we'll ignore it and then do this stuff. What do we have? Oh, we have this situation that's very similar to what we did in the previous section. Okay, you have sign in the odd power, which means that you can save one at the end. I put it at the end there with d theta because that's going to become your du. Okay, so then you have just sine and cosine, and then you shift the rest, change the rest of the sign, being that it's even power, sine squared, into the cosine by the trig identity. And then you have a bunch of cosines nicely with a sign at the end to take care of the du. So you can substitute u equal to cosine theta. This u is, did we say any u earlier? No? That's good. Okay, so then so you do your substitution, and then you don't even need to do the substitution. You just integrate it directly. Either way, so you come up with something, and then which equals to this, okay? And then you don't forget to plug in what is cosine theta. Did I write down what cosine theta is? Yeah, this comes from making the triangle again, okay? If x is sine theta, what is cosine theta? You draw your triangle and figure out that it's 1 minus x squared, which is also what the book says. And then plug that in, and this is basically your answer, but your book wants you to clean it up a little bit. All right, so let's clean it up. Where did I clean it up? On the other side. All right, so I cleaned it up right here. There seems to be a lot of bother with, seems to be a ton of cleaning, but it did eventually come out. Okay, you do all this extra algebra, and yes, add and subtract, and oh my, you have to do fractions. Anyway, so the point is eventually it's done, and I came up with this answer, which is good. Is identical to the back of the book with one exception. The back of the book, and that's why it's is this 145? Am I give me a second, did I show you the wrong problem? It's right, never mind. Anyway, so there's the answer, except that if you look at the problem on the back, you will notice that they have multiplied another square root of 6 over x cubed. Okay, why did they do that? The reason is because if you plug this problem, the original problem here, which is just this integral, into the Wolfram calculator, it will come out with the exact answer that the book showed. Okay, and if you typed it in, that's why they have that. Now, however, I have a problem with that answer. The reason they put it in is because you have to worry about the negative version. That is, the answer is actually this thing right here, if x is bigger than 0, and you slap on the negative sign in front of the entire answer if x is negative. So it's a two-part answer. And so the answer is this thing if it's bigger than or equal to 0, without multiplying that thing that your book wants to multiply. Okay, now what's wrong with multiplying that thing on there? The purpose of multiplying this thing is that it's an automatic sign exchange, because this thing, well, if you multiply in there, when it's positive, it'll be positive, and when it's negative, it'll be negative. Basically, you don't have to give two answers. It just slapped it in itself. You might think that's pretty good, right? For one thing, you don't need to say this. This is a waste of time. Okay, I mean, why does it x cubed 6 over x3 is unnecessary? It's just x. You can, for example, do. Why is my camera not focusing? There. You can, for example, do square root of x over x. That's plenty good enough. However, I maintain that you shouldn't do that. You know why? Because if you stick x at the bottom of the denominator, what happens when your x happen to be 0? Then your answer, your function is not defined anymore. Whereas the original function, without multiplying by that thing, the original function is perfectly defined for x, because there's nowhere does it. The original answer is defined perfectly fine because it doesn't have any x in the denominator. That's why the answer in the book is inferior, in my opinion. But you think, well, if we just ignore or understand that, oh, when x is 0 in the denominator, you just like get rid of that and simply take the answer itself, just plug in 0 on all this. You can argue that, but we're soon going to see a situation where you can't get away with it. That is, the calculator is cranking out something that's much worse than what you can do yourself. But anyway, so we'll talk about that later. The point is, that is the answer of problem 145. I also said that problem 145 has two ways of doing it. The other way, of course, is u-substitution. Now, with u-substitution, problem 145 ends up being, again, shorter than before. So let me show you how that's done. The only hard part about u-substitution is figure out what to call u. Now, u, in this case, we will call it 1 minus x squared. Again, you have to factor out x cubed, and remember that it has to be in the absolute value. So then we have that done. Once you figure out that set u equals to 1 minus x squared will do the trick. Then you follow the standard rules, and the whole thing turns out to be some kind of a power rule situation, see, which can then be readily integrated quickly, and then you get this thing, which you should later, of course, clean it up a little bit to look more like the answer at the back of the book. But you also remember that this answer, you have to slap a negative sign on it for when x is negative, which I didn't write down here, but that's the idea. All right, now problem one, this is 145. Okay, that is now something interesting happened with the Symbolab integral calculator that I have a link for you to use normally. And this is the first time I caught Symbolab in a mistake. Well, that is, what happens is when I plugged it in with a definite in the definite integral calculator, and I set it as from -1 to -1 to integrate it, it says the solution is 0. Now, why would the solution be 0? The reason, well, the solution can't be 0. Okay, why? Because we're integrating the square root, right? And the square root is always positive, so this answer is always positive. So how did this calculator mess up? I mean, this is a serious mistake. This isn't just like the other one where you added the divided by 0, so it doesn't work for 0, but at least it works for everything else. This is point blank wrong. Now, how does it know? How did it get wrong? Because when it pulled out the x to the power 3, it forgot to put on the absolute value. And if you don't put on the absolute value, then you got the area becomes negative on the other side. And when that happens, then the integral becomes canceled out, and then everything becomes so that the whole thing ended up being 0 because the two sides canceled out. Now, the original function, that is the square root of x6 minus x8 before the integration, looks like this. Okay, then as you can see, at least I think that's what that is. Well, whatever. There's the function. No, I think that might be, yeah, that's the original integration. And as you can see, that both the two sides are exactly the same, but in a sort of a mirror image, and it is above all positive. So there's no way the integral from -1 to 1 can be 0. So that's why I know that the calculator is definitely wrong, which means when you use these calculators, you have to watch over them to make sure they're not screwed up. And in my experience so far, the calculator has saved me a lot of time, but I also spent hours trying to figure out if the calculator is right or wrong. So you know how it is. There's a benefit and a drawback. Next, let's look at problem 147, where we're doing a different type of problem, where now we have x squared minus a squared. So to do that, we'll follow the strategy on page 293. where you are supposed to set x right on this side. X has to be equal to secant theta. Okay, and then the derivative of x then becomes secant tangent, and you have to follow this rule right here, where secant squared theta minus 1 is tangent theta. Now notice the minus. In your book, there was a slight mistake in the strategy where it wrote down plus. Okay, it's not plus, it's minus. All right, so then having said that, let's look at the bottom. Then everything just comes out pretty nicely. The then yeah, and then you plug in various things, and then I think, let's see, what does it look like? The tangent doesn't, well, why did my camera oh, my camera must be looking at me and then stop focusing. All right, so let's not show my face here so that the camera can focus. Anyway, you end up with a tangent squared. Okay, so you don't have to worry about well, actually, I don't think you have to worry about it anyway in this case. I think only one more case that you worry about. Either way, the point is, in this case, you don't have to worry about the absolute value or anything. And then because the tangent end up being squared over here, see? Because one of the tangents got canceled out. Once it's canceled out, then the tangent is squared over here and everything works out nicely, and you end up with this some kind of answer like this. And then the next page, continuing, we have and the whole thing end up being right here. Okay, that's the answer. If you draw your triangle and figure out something like sine theta, okay, you start out with secant, you gotta figure out what the sine theta is. Okay, let me cover my face so that my camera focuses on the math. Is that right? Is it focusing? Yeah, pretty good. Okay, so then that's the answer, and that is correct. And of course, in this problem, x has to be bigger. Absolute value of x has to be bigger than 3 to make sense. Otherwise, your integral is going to be, your square root is going to be negative. That should do it. And so next, let's look at problem 149. Problem 149 is similar to the one before, where we have an x squared minus a squared situation. Therefore, we will again use the strategy on page 293. And then, where x is set as secant theta. Now, in that case, the tangent theta, well, you have to slap the absolute value on there, and there's a specific statement. Yeah, okay, I wrote that down here. I didn't mention that in the previous problem, where, as according to the book strategy, it equals to tangent theta for x bigger than 1 and negative tangent theta for x less than 1. And that's important, but luckily not for this problem. Why? Because once you plug everything in right here, you notice there's a tangent theta in the denominator and tangent theta in the numerator, and that just cancels out. So we don't care if it's positive or negative, it's gone. Okay, and then your answer end up being the integral of secant cubed. Now we have done secant cubed, what, 4 times now? 3 times previously, and then 1 time in some example, I think. It doesn't matter. But by now, we're not going to go look back for some example. You're just going to look in Appendix A, all the rules of integration. Okay, this is Rule 26 for the integral of secant cubed. From now on, we're just going to look that rule up, okay, on page 700 or +8 if you are scrolling in the computer or tablet. Because the scrolling pages are slightly different, 8 more than the regular book page. Anyway, so then you plug that formula right out, which is that thing right here, okay? And then remember what secant theta is. It is the square root of whatever or something. And no, well, secant theta is just x, okay? The tangent theta is the square root of something. So you plug all that information in right here very carefully, and you get that as the answer, and you don't have to worry about positive or negative. It happened in this particular case. Tangent happens to be conveniently canceled out, so we're good. So that's 149. Okay, next let's look at problem 151, where we have the integral, now we have x squared plus a squared situation. So we're going to follow the strategy on page 289. Okay, there's their strategy where x is set as tangent theta. Then, of course, dx is secant squared. And then you figure out the secant theta is this thing, okay, which is very convenient. Then you can plug everything in, and you end up with a fairly simple looking trigonometric fraction, and then you simplify it some more, and you end up with this thing, which is very nice because you have sine squared on the bottom, and then du cosine theta d theta right there on top. Sines, the derivative of sine is cosine, so then you can just integrate that, and you end up with this thing, right? And so by now, the only thing you have to figure out is what is sine theta. If x is tangent theta, what's sine theta? Then you draw your little triangle. X is tangent theta, x over 1 equals the tangent theta. Then sine is 1 over the hypotenuse, which is the square root of something. And then you write it all down carefully and not mess up anything. And the answer is correct. Don't forget that negative sign. See a negative sign there? Yeah, do not forget it. And then you're good. Next, let's look at problem 161, where you're supposed to complete the squares. Okay, if the book wants you to complete squares, then let's complete squares. 1 over x squared plus 2x plus 1. Everybody knows that's x plus 1 squared. Then you let u equal to x plus 1, and then the answer will pop right out in your face. That's all. Okay, next, let's do problem 163. 163, which is the integral of something that looks hard, okay, the square root of some polynomial. But if we were to complete the square like we did in the previous problem, then everything works out pretty good. Okay, so let's look at the 163, where we, okay, then to complete the square, if you remember how that's done, if you don't remember, just look it up on the internet. That's in Google search, it comes out right away. It's just rewriting this polynomial in the square root into this form. Okay, and once you get that, then you notice that it is a squared minus x squared situation, right? So then you let u equal the first thing I did is do the u-substitution. So you plug in the u-substitution, and then you have this thing. And by the time you get here, we're not going to go any farther. We're just going to pull out rule 16 on page 700 of your book, 7 plus 8 if you're scrolling, right? And then rule 16 states that this type of integral is just sine inverse u over a. So you plug it right in. See, I have it right there. Sine inverse u over 5. And then plug, what was u again? X minus 5. Plug that in. That's your answer. Now in my notes, I said I think I said before that the answer in back is wrong. That's not exactly true, but I'll show you what I mean in a second. Well, if you haven't found out already, because if you have looked at the answer at the back of the book, it will blow your mind. Anyway, and it's like, what the heck is that? But we'll talk about that in a second. Okay, right now we'll just talk about this problem, and I will do it again. See, and this time we're gonna do the strategy method, which is we'll do the strategy. I don't know which page it is anymore. So let x it says on top x equal to u. No, let's scratch that. Let's x look down here. Okay, let's let x equal to 5 sine theta, which is following the sorry, what? Am I right? I think so. So that is the u or something. Well, I don't know why I did that. You get the idea. In other words, I'm trying to solve this thing right here. Okay, I just rewrite it down here. Don't know why I changed it to x. Anyway, so we're solving this problem right here, and then we let x equal to 5 sine theta in strategy maybe 286. I think page 286. Anyway, so when you work through this standard stuff, and you end up with this, right? What is that? That is, you end up, the integral is just theta, and which means theta is sine inverse of x over 5. What's x? X is u, where u is x minus 5. This is a different u, but you get my idea. The point is that come out with, using the trigonometric substitution, came out with the exact same answer. See, my answer down here, but by the trig substitutions, identical to the one slightly higher up here, where it's just by u-substitution. So being that I did it in two completely different ways, then I know that my answer is correct. Then when you look, and of course the answer is also very simple. Now when you look at the answer, if you were to use the book's calculator, well, not just the book's calculator, okay, also the answer in the back of the book, they both look something like this, even although they're not identical. You see that thing? That looks incredibly complicated, right? Now this is the answer in the back of the book doesn't have the tangent h inverse, but it still is similar otherwise. Except that it replaced tangent inverse with natural log of some big mess. Now the question is, which one is right? My simple answer, which is also the obvious answer, or this thing that the book answered in the back? And why does it come out with this? Okay, now let me tell you this answer is definitely wrong by our standards. What I mean is, when I try to plug this into the graphics calculator, the decimals calculator, it won't graph. And so I looked at it and tried to figure out, why doesn't this thing graph? And then you notice that there's an x minus 10 on top of the fraction, and the exact same thing on the bottom, except it's inverse. Okay, here's the plot of the graph. Now notice the plot of the graph is identical to the arctan, the answer I give. So this answer is correct. They must be correct in a way. However, by our standards, that's not possible because this number right here, okay? For example, is this graph, the plot, which is correct, is identical to what we have. It's defined from 0 to 10 or something like that. Okay, if it's defined from 0 to 10, let's figure out what the value is when x equal to 1. Okay, why not 0? Well, as you notice, if x is 0, this whole thing dies. I mean, it's not defined, right? Because there's an x in the denominator. So we'll ignore that for now, and let's see what happens when x equal to 1. You notice when x equal to 1, you are immediately kicked out because you have a square root of 1 minus 10. That is negative. That is not allowed by our standards right now. Okay, so the book must have done this. I mean, the calculator must have done this in some big, complicated, roundabout way that is correct by a different definition. But by our definition, we cannot integrate negative numbers. So this answer is completely unacceptable. The answer at the book has the same thing. It has x minus 10. Well, that's not okay, okay? Because the original function, as you can see here, is defined perfectly when x equal to 1. See right here? It's just negative x squared plus 10x. When x is 1, then the whole thing is just 9, right? Minus 1 plus 10 is 9. Whereas the answer is not defined for x equal to 1. So therefore, I will rule this answer as wrong. And it probably uses the complex numbers and stuff like that, but we don't care about that right now, okay? I mean, so that's the problem with the integral calculator. It's great in a lot of ways, but it also takes a hike and start doing some weird junk that is not suitable for us, and we cannot accept that answer. So if you present that answer if you present that answer in my homework, I would mark that as wrong. Okay, that's not acceptable. The arc sine, the one that I show you, the sine inverse of x over 5, that simple little thing, that is the right answer for us. Because in mathematics, the simplest way is usually the best way. With that, I think that's the end of this homework session. Oh, I should mention that so that the integral calculator on the computer is very, very nice in a lot of ways, right? Because a lot of integration is tedious to do, and the calculator can crank it right out. The problem, however, is that sometimes the calculator does weird stuff or even get it wrong, and so you can't trust it completely. Just for example, this morning, I mean, I've saved a lot of time using the calculator, but also this morning I spent 2 hours just to figure out why this problem isn't working out, why the decimal calculator isn't plotting it. It took forever to type that stuff in, right? And to type it in exactly right. and figure out all that stuff. So I also burned up 2 hours on the integral calculator that wouldn't have happened back in the day when I didn't have the integral calculator. So there's the benefit and drawback on both sides. It can save time, or you can spend a ton more time. And so if you do, I tell you this so that if you do spend a ton of time, got stuck on a calculator, don't be surprised. It happens to everybody.